Okay, hello out there. This is Unit 10 that we're beginning, our final unit in AP Calculus AB. We're going to start with Lesson 1, the area between curves. I'm coming to you live from my own dining room, and so hopefully my parrot will cooperate and not yell too much. He tends to get a little jealous when I talk to my computer instead of him. And we'll just see how it goes. So if you hear some loud parrot noises, please bear with me. All right, so today we're talking about the area between curves. So let's talk about how that's going to work out. So let's say that I have a function, and I'll just draw some random curve here called f. Okay? So that's f of x, and another function which we'll call g of x. And I would like to find the area between those curves from, let me use a line tool here, from A to B. So this area here, I can explain how this works in a couple of different ways. I think the easiest way to first understand it is that we have an area that we can find with the definite integral from a to b of f, and that would be the area under the curve from the curve all the way down to the x-axis. If I find that area and then subtract the definite integral of g from a to b, by just reducing, I'll have only this area here in the middle. Okay, so you can see that process should result in us getting the area that's above the red but below the blue. But I'd like to go ahead and look at that just a slightly different way. So that I think that's an easy way of understanding why this works. But moving forward in this unit, I want you to have a different understanding of it. I want us to go back to what a definite integral is. It is a summing of rectangles. Okay, let me get a color I haven't used here yet. I'll use this color. And if we think of these rectangles as being infinitely thin, if I subtract the y coordinate given by f of x, remember f of x is a y coordinate, minus the y coordinate given by g of x, then I get a rectangular height of f minus g. Then, from there, I can continue this process where each rectangle is a width of dx. And I just keep adding these infinite number of rectangles. And so when I subtract f minus g, I'm simply getting a height for a rectangle and multiplying it by dx, which is the width of the rectangle, which will give me this full thing. So you can either think of taking the definite integral of blue minus the definite integral of red, or you can think of it as subtracting the y's of f minus the y's of g to get your height. So let's take a look at what that's going to look like. The area then is going to be the integral from a to b of f of x minus g of x. And I'm kind of writing it in the idea of the second way I told you to envision it. But we could also split this integral up across the subtraction, and then it would be more like the first one. Sometimes it's easier, or sometimes it's easier to work with y's. And sometimes we absolutely have to work with y's because the function can't be expressed in terms of x. So if x is a function of y, then we're talking about a graph that maybe doesn't even pass the vertical line test, but it would pass a horizontal line test. So this function here is x as a function of the y coordinate. And we can have another function over here that is x as a function of the y coordinate as well, and I'll call that g of y. So you may not have graphed too much functions of y. That's typically done towards the end of an Algebra 2 or a pre-calculus class, if at all, but it's basically the same thing. So if we were going to find this area between those two curves, working with functions of y, then we're going to be looking at y coordinates for A and B, where A is the point below B here. And again, let's talk about the rectangle approach here. That when I start down here at A and I take the x value here. Now remember, the function of y gives an x coordinate. So I'm taking this far right x coordinate minus the far left x coordinate, and I just keep subtracting them to get that width, and then the height of these rectangles are dy. You can think of the instantaneous change in y is what's causing the thinness of these flat laying rectangles, these wide and very short rectangles. And I sum all those up and it'll give me the area. And like before, if you didn't notice, I don't know if I made that a key point, but the graph on top minus the graph on bottom is what we need to do, or else we'd get the negative area. We're going to do the graph on the right minus the graph on the left. And that's going to be in terms of dy. And here, A and B are y coordinates, not x coordinates. Now, the nice thing about this, though, is it doesn't matter if one of these functions is got to the left of the y-axis and gives a negative integral. It still works out perfectly. This will always give the correct positive area as long as you do the right curve minus the left curve. All right, example 1.1. Here we go. We're going to draw a figure, and we'll shade the region bounded by the graphs, and then we'll set up an integral expression that can be used to find the area. When you're solving a problem like this without a calculator, you need to focus on the important parts of drawing a sketch. And if they don't say draw a sketch, you should probably draw one anyway. The important part of your sketch is you need to know which graph is on top of which. You also need to know where they intersect. Quite often you can find where they intersect just as you graph it or by guess and test, but we'll go ahead and set up an algebra equation to see if these intersect anywhere. They actually are not going to intersect, it looks like, but I'll go ahead and let's go ahead and graph. This is x squared plus 2. And again, it does not matter that your graph is perfect. We're graphing a sketch to get a mental picture and so that we can know which graph is on top of which. And like I said, it's important to know where if they intersect, but this equation here would not have any real solutions. You can do the quadratic formula if you like, but it's not going to happen. And so we're just looking at two curves like that. We're going from x equals 0 to x equals 1. And we'll be finding this area here. All right, so let's do it. The curve on top, you can see, is x squared. I'm going to get rid of this equation here. So since we already considered it and they don't intersect, they often do though. X squared plus 2 is the curve on top minus the curve on bottom. And I usually put it in parentheses. This case it's only one term, so I didn't need it, but quite often you do need parentheses around the second equation. And that whole equation is times dx, and we're integrating from 0 to 1. Let's just go ahead and do the integration now. X cubed over 3 plus 2x plus x squared over 2. And we'll be performing that from 0 to 1. So it gives me 1/3 plus 2 plus 1/2. And I can let you finish that off on your own if you want. If you need to simplify it, say for a multiple choice. But otherwise, you do not need to simplify it. All right, let's do the next one. We're going to look at 3 minus x squared and negative x plus 1. So 3 minus x squared has a y-intercept up here at 3, and it's going to open downward. And then negative x plus 1, well, that's clearly going to have some intersection points, so we better go and find those. So let's set them equal to each other. And I get x squared minus x, I think minus 2. So x equals 2 and x equals negative 1. So at x equals 2, we have y coordinates of, looks like negative 1. And at x equals negative 1, we have y coordinates of, I guess, 2. That's kind of funny. Just kind of flip-flopped. All right, so to find the area, we'll be subtracting the parabola minus the line, and we'll be integrating on x coordinates from negative 1 to 2. So we'll be doing the integral from -1 to 2 of 3 minus x squared minus a negative x plus 1. And then that whole thing times dx. I will go ahead and simplify this just a little before I start integrating. It gives me a negative x squared plus x plus 2. And when we integrate that, we get a negative x cubed over 3 plus x squared over 2 plus 2x. And we'll be doing that from -1 to 2. Just going to give myself a little bit of room here. Scroll down here. All right, so this is a -8/3 plus 4 over 2 is 2 plus 4 minus, that's going to be a positive 1/3 plus 1/2 minus 2. And again, I'll let you simplify that. Hopefully that's something that you don't find too difficult to do if you absolutely need to. Okay, let's go on to example 1.3. Oh, just one quick point about simplifying. On a free response question, remember, you can't leave it like this. You need to go ahead and plug in the 2 and the -1. I actually did some simplifying as I went. You don't need to. You can just put parentheses for each one of those x values and replace it with a 2 and then put minus. You need parentheses around the entire second part, though, and put -1 in there. You don't need to do any simplifying if you don't want to. But oftentimes these do appear sometimes as multiple choice questions, and so you'd have to be able to do it to get an answer. Okay, find the area bounded by the graphs of 5 minus y squared and x equals y minus 1. Okay, here it is. We've got our x as a function of y. So parabolas that we're used to opening up and down now are going to be opening left and right. And because it's a negative y squared, it's actually going to be opening to the left. We can get a pretty good idea of what's going on by simply solving to see if there's any intersection points first. Setting this equal to 0 gives me y squared plus y minus 6, and I have y plus 3 and y minus 2. So y equals -3 and y equals positive 2. When y is equal to -3, we're going to get 5 minus 9 is a -4. So -4 on the x goes with -3 on the y. And then when I plug in -3 here, it also gives me -4. Let's try the 2. 5 minus 2 squared is 1, and 2 minus 1 is also 1, so it works in both places. So y of 2 goes with x of 1. And we know that those are 2 points on this leftward opening parabola. The 5, by the way, ends up being this x-intercept. And then we have a line, which is a slope of 1 going up like that. So we can see the points of intersection. They are at -4, -3, and 1, 2. We know that we need to subtract the right graph minus the left graph and sum all these rectangles. So this will be the integral from, remember, we're doing y coordinates, are going from this bottom y coordinate to this top y coordinate. So from -3 to positive 2 of the rightmost graph, which is 5 minus y squared, minus the leftmost graph, which is y minus 1 dy. And then from here, we can just simply do our calculus, maybe simplify a little bit, and find our area. So here, that'd be a -y squared. Looks like a minus y. And then plus 1 plus 5 is plus 6 dy. So -y cubed over 3 minus y squared over 2 plus 6y. So -8/3 minus 4 over 2 is 2 plus 12. Now I'm doing the -3, so that would be a positive 27 over 3, which is actually 9, minus 9 over 2, minus 18. And again, I'll let you finish that on your own if you need it. All right, let's go on to example 1.4. Okay, if you're following along in my note handouts, early versions of my notes had a minus here. I've gone ahead and erased it. This curve has definitely not got a negative slope. It's just a typo. So we're going to use our calculator to find the area that is enclosed. And you'll notice there's two of them. You'll also notice that where they are, which graph is on the right-hand side, since we're looking at x as a function of y, it's the line at one place, and it's the cubic polynomial in another region. So we're going to have to handle the fact that they switch. So we'll pay attention to how we do that. First thing you need to do is find these points of intersection. Quite often on the AP exam, they won't even give you these numbers here. They'll just give you a quick little picture of it. We need to be able to use our graphing calculator. So we'll do that. Okay, I got just a little emulator going here. Let's go to y equals, and I'm actually going to graph these as functions of x so that I can use the intersection tool, because my calculator won't allow me to graph them in terms of y. But I'm okay with that. I'll just graph their inverses, and wherever their points of intersection are, I'll just switch the x and y values. These are also pretty easy to use the solve tool on, and you could solve them relatively easily, but this would not be very solvable by hand. Okay, there we go. We have our graphs coming, and you'll notice that it is kind of been rotated. Right? It's not exactly the same picture, but they're related. And we'll find the intersections. So I go to the math menu, which is F5, and also choose intersection. It's extremely important that you're able to find the zeros of a graph or the intersections of two graphs. Those are two of the four things you absolutely must be able to do with a calculator. The other one is you have to be able to use a numeric integral and a numeric derivative. So I'm just going to, it's going to ask me for the first curve, because you could have more than one curve graph. So just hit enter to select it. It's asking me for a second curve. You'll notice it automatically toggled to the second equation, so I can just hit enter. And it's going to ask me for a lower and upper bound, and that always means bounds on x. So I wish it said left bound and right bound, but it's lower, and it doesn't have to be below the intersection. It just has to be to the left of it. And then I arrow over to where, and I'm kind of writing the line here. It doesn't matter. You can use either one. Just keep going to the right until you are past the point of intersection, and make sure you see the word intersection. That's absolutely necessary. Let me make this to where it's just temporarily, it's always on top, so that I can write without losing it. Okay, so this is, now remember, the negative 2.13 is actually a y coordinate for us, and this is actually our x coordinate. So I'm going to label this negative 3.257 comma negative 2.128. All right. Next, we need to find the other point of intersection. So I'll go to F5 again and choose 5 for intersection. Select my two curves. Unless you have more than one curve, more than two curves typed in, you just have to hit enter twice. Lower bound, and then I just press my arrow till I get to the right of this intersection. And here we go. So again, remember, these are backwards. I kind of add that extra little trick to it. I had to tell you the truth, I've never actually seen them do this to you on the AP exam. Usually, if you have to use your graphing calculator for intersections, they're always y as a function of x, but kind of killing two birds with one stone. All right, teaching two topics at once. F5, let's do one more. Again, just toggle. All right, lower bound it's already to the left of this third intersection point. And here we go. So again, remember, these are backwards, as you can see in the graph here, that these line up. 5.6601 and 2.300. I think that's a 6, right? Let me bring that down here. 2.3301, I'll say. Okay, now we're done with this thing for just a little while. We have two options. If we did not have a calculator, our only option would be to actually find the area in this lower portion here, and then the area in this upper portion here, splitting up the integral, and then adding together. But because we have a calculator, we can do a nifty little trick. We can find the area enclosed by two curves by using the absolute value. So I'm going to say the absolute value the integral of the absolute value of their difference. And in this case, it doesn't even matter which one I put first. Just make sure you do put subtraction with a parentheses, a pair of parentheses around your second equation. And so all that's in the absolute value. So we do that kind of thing a lot, particularly in physics problems. Okay, now I'm going to be integrating from the lowest y coordinate, so that's a negative 2.128, up to the highest y coordinate, which is a positive 2.3301. Now let's see how I type that in. So I go to my home screen here, actually, and one of the things I'm not sure if it does on this problem, but when you start putting absolute value inside integrals, you will oftentimes get an error message from the TI-89 saying, I can't do this problem. It's too hard. Loss of precision, and sometimes it won't even give you an answer. In that case, you really need to be able to use a numeric integral. So I'm going to go down and find numeric integrate. And the problem with numeric integrate is it doesn't give you a nice, pretty print that we're used to. So you have to be real careful. Int. All right, so we're going to do absolute value, which is second 5. Basically, everything can be found in the math menu, to tell you the truth. Even algebra, trig, calculus, everything is in the math menu if you're looking for something like there. Also the catalog. Number is where this one is. So we're going to be looking at absolute value. Be careful not to think it's this bar next to 7. That's the such that. That's not the absolute value. So y cubed minus 3y minus parentheses 2y plus 1. Oh, something didn't happen. 2y plus 1. All right, so that parenthesis closes to 2y plus 1. I need another parenthesis to close the absolute value. Now, comma, I need to give it the y coordinate, the y value, because we are going to be integrating with respect to y. Then I need to give it the lower bound, negative 2.128, comma, the upper bound, 2.3301. And I close that off. And here we go. And it is working hard. I'm not sure if this emulator can do it as well as a real life calculator. Might get stuck, but we'll see. Oh, there it goes. 12.801. Now, if you do not use the numeric integrate function, just want to show you if this might give an error. I'm curious if it does. So if I try to just use the second 7, curious what happens there. Might give us the right answer. So it's just sometimes it doesn't. And if we can, I know one of the homework problems, you'll get the error. See, it's thinking pretty hard. That's the other thing. The numeric integrate is faster, and it took a while for us. Oh, there it is. They did not give the answer. Do you see that? It just spat it right back to me, saying I can't do this with my normal integrate algorithms. You need to use a numeric integrate. So very important we have that down. Okay, let's take a look at the next ones. Okay, you get some practice problems. So I'm going to have you go ahead and do practice 1.1, practice 1.2. A and B, and then you have 1.4, and that should finish it off. So please work each one of these problems. Use your calculator when it says to, and we will then go over the results. So we'll start with practice 1.1. All right, hopefully you've taken an opportunity to try this. This is a graph of cosine x squared and x squared minus 1. We want to write and evaluate an expression for the area bounded between the two curves. So we're going to need these points of intersection. Luckily this time we don't have to switch the x and y values. So I'll start with cosine. And keep in mind, if your calculator does not say radians, you will not get the right answer. We don't ever do calculus in degrees. It's a disaster. All right, and then on the next one we have x squared minus 1. And I am going to show you a couple different things you can do here when you graph this. you need to know zoom, that's the F2 button, and then 6 is zoom standard. It gives you that pretty normal negative 10 to 10 look. Negative 10 on the X, negative positive 10 on the X, negative 10Y, positive 10Y. You need to be able to also use this window. That's Diamond F2. It's kind of hard to see on this small little calculator, but Diamond F2 allows you to actually type in the X coordinates. So we could try and match the values here. But most of the time, not always, but most of the time, it is easier to just use zoom one. So if you're gonna know two buttons in zoom, those zoom standard, just zoom 6 and zoom box. Remember, those are the F keys when you're in the graphing menu. These function keys at the top. And you just have to draw one corner of the box and then an opposing diagonal corner. And you just want to put your corner, so you hit enter to start it, to where you make a box that contains everything you want to see. And the box will be your next viewing window. So my graph is going to look like it's zoomed in right there on that box I just created, which is perfect for us. Now that we've got that, it should be easy for us to use our F5 commands to find the intersection points. So I'll say intersect. Again, first curve, second curve. I've only got two curves in there, so just toggles between the two. Lower bound means to the left of the point of intersection, and upper bound means to the right. And we'll label these points. Specifically, I just need their X coordinate. This is, but I'll go ahead and label the X and the Y, I guess. Negative 1.1329 and 0.2834. All right, let's go get the next one. F5 for the math menu, 5 for intersection, first curve, second curve. And we're going to arrow over to where we're to the left. We could probably just pick it already, but I like to get a little closer. And then just to the right of the intersection. Okay, so that's 1.1329. Because it's even, makes sense. And 0.2834. Oh, I'm two even functions, so it makes sense that they would be symmetrical in their points of intersection. That's satisfying. Okay, let's integrate. We're going to be doing the top equation, which on this interval is cosine of x squared minus the parabola. Make sure you put parentheses around it. Dx, and we'll be integrating from the lower x bound, which is a negative 1.1329, to the upper bound, which is 1.1329. Okay, so I could use a numeric integrate. I do want to go ahead and show you the regular integrate function. If you don't have absolute value in it, I've never had a problem with it. So it always eventually gets me an answer. So second cosine x squared. Make sure that squared's on the x, not on the cosine. It's got to be inside the parentheses. Minus parentheses x squared minus 1, comma, I'm using x, comma, negative 1.1329, comma, 1.1329. And I like the regular integrate because we will get the pretty print to look at, and you can even arrow up and see what's, got cut off, and really gives us a chance to check that we've entered it in correctly. 3.216. Make sure you use at least 3 decimals for your answer. Okay, let's go down to practice 1.2. All right, we're going to find the area in the first quadrant bounded by the graph of y equals 1 over x, that's the blue curve, and the graph of negative x squared plus 4. So we'll go to our y equals again, and we'll graph each one of these. So 1 over x and negative x squared plus 4. And we could go back to zoom standard and then use our zoom box. But let's practice a different way. We're going to go diamond F2 with in green here is the word window. I know it's difficult to see here. And I'm just going to try and match close to the window that they've shown in this problem. Then X max of 4. The scale, you never have to worry about the scale. That's just what the tick marks go by. It doesn't affect anything. -1 for the min. We've got too many negatives. And we'll go to 4 on the max. Oh, I need to give myself a little bit more room because I'm going to get an intersection. So I'll say 5. And let's take a look at the graph. By the way, when you graph, if you ever get something like error range or something like that, you want to be cognizant of the fact that that's probably because you did something like put an x min of you meant to say -10 and then x max of 5, but you accidentally put +10. Whatever happens, you put your min value above your max value is usually what that means. All right, let's go to F5 and we'll get our intersection. And first curve, second curve, and lower bound. And there's a little bit more of the curve over here. It looks like. I'm not sure what that is. But we want just this part right here. That could have been the asymptote accidentally drawing. Sometimes the asymptotes get accidentally kind of drawn, but just ignore it. Upper bound here. Okay, 0.254. That's this x value here. And I won't write down the y coordinate because we really don't need it here. And we get the second intersection point. .86, we'll say 861. So we're going to be finding the integral of the top curve, which is the -x² plus 4, minus the bottom curve, which is 1 over x, dx, and we'll be integrating from 0.254 to 1.861. So that gives us another chance to practice doing an integral. Second 7, I'm not going to use numeric integrate because I don't think I have to because I don't have something like absolute value in there. -x² plus 4 plus 4 minus 1 over x. We're using x from 0.254 to 1.861. One other note, it's very important that you always write down your integral on a free response question. Even if you go on to evaluate it, you need to make sure that you've written it down. It's a way of documenting your work. And don't write down what you would put on a calculator. Write down the true math version, the pretty print, if you will. 2.294 is our answer. All right, let's go to the next one. Okay, so I have a kind of an extension here where we're going to be applying these concepts to some of the physics problems. The velocity in meters per second of a particle for t from 0 to 8 is given by this expression. We're going to write and evaluate an expression for the displacement of the particle over the time from 0 to 8. So the displacement is simply the change in position. It's quite possible that the particle could travel a great distance but end up back where it started, having a displacement of 0. That's simply summing all the velocity. So displacement is the integral of velocity. We'll be integrating from 0 to 8 of -t times sine of pi over 8 t plus 2. Let's go ahead and type that in the calculator. You want to be really careful about saying t sine. Make sure you put in a multiplication symbol there, or else it's going to think you're trying to, because you can define your own functions in this calculator, and you could call something t sine. So you need to make sure that you include multiplication. In general, when in doubt, include a multiplication. Don't assume it can do the applied multiply. Sine of pi over 8 times t plus 2. And I realize I am missing my dt, shame on me, comma t, comma 0 to 8. Oh, I wanted decimals. Diamond in there. I'm still thinking. Okay, so this value is negative 4.372. And what does that mean? It means at t, we could just say the displacement is negative 4.32 meters. I'll put a meters here. But I'm going to say at t equals 8, the particle is 4.372 meters behind where it was at t equals 0. It's about location. The location is negative 4.372 relative to its start. All right, next it says write an expression using absolute value to express the total distance. So since distance is the absolute value of displacement, we're going to find the absolute value of the integral. So that's what I wanted to point out is this technique we use for finding the area when two curves kind of crisscrossed multiple times. We can use that here quite effectively. So I'll do the absolute value. And it's extremely important that you put the absolute value inside the integral. Otherwise, you're just taking the absolute value of displacement. You need to take the absolute value of the velocity and then integrate that. And like we said before, that is something you want to do in a numeric integrate. So let me go to F3, the calculus menu, and I'm not sure which number it is, at letter A or B, something like that. Okay. So we'll be doing a numeric integrate. Let me get rid of this here. And we'll be saying second 5 to go to math, number, absolute value. And I need to close off the absolute value parentheses right here. And we'll see how it goes. Still thinking. And this kind of emulated one's not really as good. Hopefully yours is, your true T89 hopefully works a little faster. Traveled a distance of, so the meaning is the particle traveled a distance of 12.026 meters over t equals 0 to t equals 8. So that's the difference. Not displacement, but distance traveled. All right, let's take a look at the next one. So let's consider the graph of y equals x squared and y equals 18 minus 3x. I want to set up an integral expression for the area bounded by the x-axis, the graph of y equals x squared and y equals 18 minus 3x using x and dx. Really important that we're careful what region we're talking about here. The x-axis is down here. This is x squared. This is 18 minus 3x. So we are talking about this region here. Okay? And they intersect clearly at down here at 0, 0. That's where this intersects the x-axis. So if I'm going to be using dx, I'm going to need to split this up because I've got two different curves. So I'm going to be using the integral, and the top curve here is the x squared. And the bottom curve is, well, just the x-axis. So I just need x squared dx to get the integral, to get the area between the curve and the x-axis. And I'll be using that integral from 0 to 3. Plus, I'll be doing the integral now from 3 to 6 of 18 minus 3x dx. That will be the final one. So that's it using x's. But interestingly enough, we can actually do this more easily, or I don't know easily, but we could do this in less integrals if we work with y's. So I'm going to just grab this and move it up. So hopefully you got that in your mind. I'm going to move that up right there so that I can look at the picture while I do this. Okay, so if I was to solve this for y, I would actually get the plus or minus square root of y is equal to x. But since we're dealing with positive x's, we'll just take the principal square root. And then solving the second equation for x gives me y minus 18 over a negative 3 is equal to x. So now I can integrate from 0, the y-coordinate 0, to the y-coordinate 9. I need to use the rightmost curve, which is actually the line, so y minus 18 over negative 3, minus the leftmost curve, which is the square root of y dy. And that's extremely important that you're able to write integrals in both ways, especially when we move on to the next few lessons in this unit. All right, and that is all for this lesson, and I will see you in the next one.